Let's learn what materials we use to make an LED and why we don't usually use silicon or germanium diodes. Now, we've already seen in a previous video that LEDs or light emitting diodes are basically PN junctions. And the way they work is when you forward bias them, that is attach a positive to the P type and a negative to the N type, the electrons and the holes start recombining. And when they do that, the electrons move from a higher energy level to a lower energy level. And in the process of doing that, they start giving out light. But the question we want to address is, what does the color of this light depend on? Well, we may have already studied in Bohr's theory that the energy of the photon released, let me just write that over here. The energy of the photon released is the difference in the energy between the transition, the difference between these two energy levels. And in our semiconductor, that's going to be the band gap, the energy of the band. I mean, energy difference between these two bands, right? So that energy of the photon is going to be the energy of the band gap. And we've seen that that should equal h times f, where f is the frequency of light, which decides the color. And so immediately you see that it's the band gap that decides the frequency of the light that gets emitted. If you have a very large band gap, you can see that the frequency of the light emitted will be high. High frequency corresponds to blue light or violet or even going to ultraviolet. And on the other hand, if you have a very small band gap, then you will end up having lower frequency, which corresponds to red or infrared or even lower. So what controls the color of the light? It's the band gap, the difference between the conduction and the valency energy levels. All right, now let's get a little technical. We could ask, what should be the value of the band gap? The number, I want the number. Okay, what should be the value if I want the frequency to be within the visible range? Well, then we just have to plug in and calculate. We know what the frequency, or we can just Google that. We know what the frequency of, the visible, what is the range of frequencies for visible light is. We can just plug that in and get the required band gap. And if you do that, we'll not do the calculation, but if you do that, then it turns out that the band gap should be somewhere between 2 electron volt to 3 electron volt. If the band gap is less than 2, we are now going into the infrared region. Even less becomes even, it goes to microwave and so on. And if you go above 3 electron volts, now you're going towards ultraviolet region. And even above that, we now enter into X-rays and gamma rays. Okay, now let's look at the band gaps of the semiconductors that we already know. We know about 2 semiconductors, silicon and germanium. Let's look at their band gaps. Turns out silicon has a band gap of about 1.1 electron volt and germanium about 0.7 electron volt. Now, can you pause the video and think about why we don't use silicon or germanium to build our LEDs? Pause and think a little bit about this. All right, the answer is in front of us. If you want the visible, the band gap should be within this range. But look at the silicon, it's 1.1. It's not even infrared, it's going into microwaves. And germanium is even worse. So we can't build an LED just by using silicon or germanium. And so the question now is, what do we do? These are the only 2 semiconductors we're aware of, right? Well, people soon figured out that you can mix elements and create your own semiconductors. The most common example, there are many examples, but the most common examples are by mixing group 13 elements with group 15 elements. For example, you can go, you can mix gallium with arsenic, or you can mix gallium with phosphorus, and you can make new semiconductors. And if you do that, turns out their band gap, for example, gallium arsenide, a mixture of gallium and arsenic, that gives you a band gap of about 1.4. And if you mix gallium and phosphorus, that gives you gallium phosphide and gives you a band gap of about 2.3. Higher band gaps than our usual semiconductors. So gallium arsenide is 1.4 and it's still not quite there, but this is useful for infrared. We're now in the infrared region. And gallium phosphide, now it's in the visible region. 2.3 turns out to be somewhere around green. And of course, you don't have to remember any of this, but you get what I'm talking about, right? Why you have to use different materials now. But what's more interesting is that people found out that you can now mix these two make another compound, an alloy, for example, or actually an alloy, mix these two, and depending upon in what proportion you mix it, you can even, get a bandwidth anywhere between, band gap, anywhere between 1.4 and 2.3. What that means is, say for example, you want to get 2. Then you mix a little bit of arsen, this one, you mix with a little bit of that one, depending upon change, tweak the ratio, and you will get 2. If you want 2.2, add a little bit more of phosphor, gallium phosphide. If you want about say 1.7, add a little bit more of gallium arsenide. So by changing the proportion of gallium arsenide and gallium phosphide, you can now get any band gap between 1.4 and 2.3. And this alloy is what we usually call as gallium arsenide phosphide. And depending upon what ratio you use of mixing gallium arsenide and gallium phosphide, you can get anywhere between 1.4 and 2.3. And that means you can now build any LED from red color to green color. So you can build red, orange, yellow, green, all the way up to green, but not blue. People were struggling to get blue color because you require even more band gap for that. And finally, a group of scientists were able to crack it. They took gallium and mixed it with nitrogen, and they ended up with the material now which is called gallium nitride. And gallium nitride ends up having a band gap of 3.4 electron volt, high enough to give us our blue LED. This was such an important discovery that they won a Nobel Prize in 2014. And I want you to take a moment to think a little bit about this. Why was it so important to manufacture blue LEDs? I mean, yeah, we had already manufactured all different other colors. Blue was the only color remaining, but why was it so important that they got a Nobel Prize for that? Can you just pause and just wonder about this for a while? Well, because with blue, we could now manufacture white LEDs. Think about it. Normal bulbs give you white light because they give out all the colors of light. But LEDs don't. Because they're working at a quantum level, they're monochromatic, right? They only give you one color of light. So how do you manufacture white? Well, you do that by mixing different LEDs. So you might have already seen this color mixing, right? Color mixing diagram. If you mix red, blue, and green, you get white. So one of the ways of building white LED is you take a red LED, take a green LED, which you can build using these two, and then mix it with blue LED, and together they shine and give you white light. Or another method that we use is you just take a blue LED, and on top of that you put a yellow phosphor layer. Now when you shine light, some of the blue is converted into yellow by the phosphor layer, and what your eye sees is a combination of blue and yellow giving you white. And let me show you a picture of that. So here you go. If you open up any of your white LEDs, you will see something like this. This is the PN junction, and that yellow is the phosphor layer on top of this. And beneath this would be a blue LED, and together that you get white light. And so with the manufacture of blue LED, we were not able to make white LEDs. And because of that, we could now replace our normal bulbs. We can make tube lights, and we can do so many other things. And that's why it was an extremely important invention. And so just to summarize, the most important thing we realized is that the color that LED gives you depends on the band gap. And we realized to get visible, you can't rely on silicon and germanium because they have just too low band gaps. And that's why people relied on getting artificial semiconductors by mixing group 13 and group 15 elements.